Yeah, last time we were talking about genetic algorithms, our first specific type. Right, and we spent some time talking about the idea of fitness and how we can go about calculating it. One of the ideas was counting the number of ones. And the other idea was just, well, optimize what it means, like what that binary number means in decimal. And both will work, but maybe there's pros and cons to each, right? We saw one that, well, you know, the changes in the, like, it might make changes in the phenotype space, getting closer to the optimum easier. Or maybe, you know, like that gradient or whatever we'd want to call it in the decimal space is better. I don't know. They're different. And in this scenario, because it's such a simple problem, like optimizing the number of ones in a string of zeros and ones, it's a silly problem, right? Like you would never use a GA for solving this problem because somebody else will just show up and just give you a whole bunch of ones and beat you. So yeah, we're not doing it. But because it's a simple problem, we know. We can clearly see, like, okay, we clearly, completely understand the genotype space and phenotype space. Like we can put our finger on every possible value we get. And that gives us some intuition towards, like, well, what might be a good way to decode or calculate the fitness. But in practice, when you're solving problems, like potential real-world problems, where nobody has a good solution, or no one has the best solution, maybe we all have pretty good solutions and we're still working on finding better ones, if we're dealing with those problems, it's probably not going to be obvious. You're probably not going to have a sense of, like, I think that fitness function is going to be better. You might have intuition behind it, but it's certainly not going to be as obvious as this example of just optimizing the number of ones in a string. So I'm just making sure that this toy example, because it's a toy example, we know a lot more about it than other problems. And it could be, like, and similarly could be said for TSP. TSP, I mean, it's a great problem, but like I was saying before, in the context of evolutionary algorithms, not a particularly interesting problem. Some people totally will use that. Maybe they're looking for a better TSP permutation, but there are some approximation algorithms that are probably going to be doing better. And so maybe you're trying to optimize a TSP problem with your GA, and that's fine, and that's what you're going to do for your assignment 1. But a lot of times, if a computer scientist working on evolutionary computation is using TSP, it's because it's one of the classic quintessential problems for benchmarking, where you've got your really good algorithm for your GA for solving TSP solving, and you do, and we want to see who's better. Well, let's use TSP. It's a great problem for this. But if I am getting, like, no one's going to hire me to, well, I mean, maybe they will. It's not a great example. But it's unlikely that it's just not a particularly good problem that maybe in practice we would actually go and take these well-studied algorithms and well-studied problems. Usually we're taking these big, beefy computational intelligence algorithms and we're applying them to things where it's like, well, I didn't know what else to do, so I tried a genetic algorithm, right? So just putting that into context. Like, let's find nonlinear relationships in fMRI data. How do you do that? I don't know, maybe I can use a genetic algorithm or a genetic programming to do it. And then I did, and it worked. Cool. The search space is insane. I don't really know what the hell's going on there, but it works, right? So just to give you a sense, really simple toy problem, zeros and ones. TSP, complicated problem, really hard problem, but still kind of like a toy problem in this space. And then there's like the real problems where, well, we actually are interested in those problems and applying these types of algorithms to them because we don't really have a better choice. Okay, selection. I think this is where we picked up last time. Randomly select a pool Take the top one as the parent, do it again. Now you have two parents, awesome. And I spent some time last time where if the pool is size 5, that means the 4 worst chromosomes, let's pretend there's no ties in fitness, the 4 worst candidate solutions can never be a parent. Because if I pick a subset of 5 and I take the best one of that 5, it's not possible to pick the 4 worst. Where maybe we want to be including some of the not as good ones, because remember, if we hit run, and we're letting our algorithm run for a day, and we are now at 12 hours on the running mark, the worst solution is still probably a pretty good solution. So we might want to include something that's, maybe there's something important in that permutation of cities that I kind of want to keep within the population, because otherwise it might converge too quickly. We don't want our algorithms converging too quickly. We want to make sure, like if I hit run and I want to come back in 24 hours, it's still making progress. If I see that curve go up to like this at the 1 hour mark, and then for the rest of the 23 hours it moves like nothing, maybe that's a bit of a waste. I gotta tune all those parameters to get things right. But more examples of that as we go, and I will do an example of solving this 0 and 1 problem. So select, population, pool size, randomly select chromosome to fill the pool, find the chromosome with the highest fitness or smallest, whether you're optimizing, like minimizing or maximizing the number of ones, minimizing Euclidean distance, whatever. Mutation, simple bit flip. This will work here. I don't need to get fancy with that pick 2 and flip, because it's not, the numbers aren't supposed to be unique, right? So I could just pick a single bit, and if it's a 0, make it a 1. If it's a 1, make it a 0. Why? Because it's easy. I like easy. Perfect. I selected this one, and it turned into a 1. Wow. So randomly select an index and flip the bit. Crossover, 1-point crossover is probably a good choice here. Select some index randomly, and then at that point, do the crossover. Hopefully I've got a good image to kind of show. Yeah, well this kind of gets, I think the vector graphics got a little weird with the strings, but whatever. If the top parents are fully red, fully blue, you pick that point, you just flip everything after that point. Great. So crossover, 2 chromosomes, select random index. For each index after the selected end, swap genes between the chromosome 1 and chromosome 2. Gene is just the single value. So switch all the 0s and 1s from this one with the 0s and 1s from this one after that index. That's it. These are just an example of 1 mutation, 1 crossover. There are a bunch more. Some are good in certain scenarios, some are required in certain scenarios. Sometimes you don't really know what's the best option. Sometimes you just like to go with the simple one because it works pretty good. Sometimes you might want a crossover that's more destructive. Or maybe you want one that's less destructive. These are terms we'll talk about a little bit later. But there's a lot of choices that we have here. Remember, everything about evolutionary computation is very, 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 very modular. How do you want to do crossover? Well, here's a whole bunch of popular ones. If you have your own idea, go for it. Do whatever you want. If it works and it gives you good results, awesome. That's what we care about. And now a generation. How are we going to do this? Well, to execute a generation, there's a lot of ways to do it. And the 2 big ones we're talking about, the steady state versus the not steady state, the one I was calling the discrete one. I like the discrete one. It's easier to me. You have a population of size 100. You create a new empty population of size 100, but it's empty. Pick 2 parents. Maybe they do crossover, maybe they do mutation, but put them over here. Select again. Again, do that a total of 50 times, I guess, to get 100. And then that new population becomes the current population, and then repeat, 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 repeat. Calculate the fitness, okay, yeah, so here's the idea. Calculate the fitness of the population, select the parents, check if we're doing genetic operators, and then add the children to the next generation. Repeat until the new population's full. I mean, here's my pseudocode-ish stuff. What do we got? Generation pop, pool size, X rate, mutation rate. X is like crossover rate. It's a common abbreviation. So what do I have? Create a new generation population array, calculate current population fitness. For each spot in the new population, select 2 parents. Ooh, that shouldn't be. For each, maybe I should make it like a new population isn't full. But anyways, select 2 parents, copy the parents. We always want to copy. Watch your references. Right? Because otherwise you're going to end up with a very big nightmare. Raise your hand if you remember the difference between a variable that's a pointer / reference versus like the actual value. You know what? I'm going to take a second just to go over this, just to make sure it is abundantly clear. If I have an array, and this can depend on programming languages, depending on how you do it. But if I have, think of memory like this. You know what? I've got a better way to do this. I've got it in my notes for 161, and I like it, so I'm going to use that instead. That's when I get to lists. Nope, no. All right. Pretend we have RAM. Now, typically we index with hexadecimal and whatnot, but I'm being lazy and just pretending it's decimal, okay? Each address in our memory has a number associated with it. Like there is a memory address. This is, by the way, this is going to be a simplified view of what's happening, but this will give you the intuition of the difference between like the value and a reference to something. Pointer, whatever you want to call it, depending on the language, it could be different. So we have RAM. Let's pretend it goes on forever. And they have like memory address locations, okay? And then I can put the content in there. Depending on the type of the content, it might take up different amounts of size, but let's pretend everything fits nicely in one cell, okay? So if I have, let's see, a variable, let's say I write in my code x equals 17. All right, so your computer's going to go find an open spot of RAM and says, oh, memory address 126 looks good. I'm going to give that address the label x, and the value that I'm going to put in there is the number 17. So the number 17 is in memory address 126, I guess, in this example. If I write y equals x, here's what it does. So the computer's going to go, oh, okay, well, I need this new variable y. Let's put it in memory address 129. Why? Because. And what do I want to do? Well, I'm going to take the contents of x and put it in y. Listen carefully. I take the contents and move the contents. That, what I just said right there, is the same. Whether I'm talking about values or pointers, what's in that memory address is copied. So people end up getting up all in their head, getting confused about which is which. You're thinking too hard. Remember, computer scientists are dumb. We need simple, simple, simple. Sorry, I hate to tell you. So, simple. Copy the contents of what's in that memory address. Now, the problem arises when, here, let me just click this. The problem arises if I want to make like an array of integers. Because, well, you know, I was able to cram the integers in those memory addresses, but if I want an array, I can't shove a whole array in one of those memory addresses. So what I'll do is I'll find this nice contiguous chunk of RAM, classically speaking. This nice contiguous chunk of RAM, look, the computer's like, look, great, I found 677 all the way to 684 is great for my array of A, B, C, D, F, G, H. I've got an array of those values. So in memory address 677, I've got the value A, 678, I've got B, yada yada, 684, I got H. That's what's in there. Okay? So this is the scenario. So this is creating the array, but what ends up happening is this. We end up, if I said Z equals this new array, the computer goes finds a nice chunk of RAM to put the contents in, and then I have the variable Z, but the variable Z that is stored in 131, it doesn't store the array. It stores a reference or pointer or whatever language in the jargon we use. It stores the information about where that is. And this is going to be true for like objects in general. Kind of. Let's forget C++ for a second. So this is how it's going to be set up. All right, so if I say Z, right, well, it's a reference that gets me to the start of the array. So what is the contents of Z? It's the address 677. Okay, the computer knows it's not the integer 677, it's the address 677. So if I come along and I write, let's see if I've got, please have the example, perfect. If I write W equals Z, what does the computer do? Well, the computer will go find room for W in RAM. It will take the contents of Z, which is the array. It's the address, right. We copy the contents of that variable over, which is just the reference to the beginning of the array. Now we have an alias. Now we have two variables that point to the same thing. Remember that I said, when I said y equals x, we copied the contents of x and put it in y. When I said w equals z, I copied the contents of z, put it in y. Or no, in w. It's the same. But by acting the same, we get a little bit of a different scenario. There's an outcome. Because I can say y equals 18 and x is left alone. But now if I say w at 0 is now j, well, I've changed that one thing, but it's like changed for z and w, right? Point being, let's bring this back to evolutionary computation. If I just copy over the reference or the pointer to the chromosome, and let's say I do a genetic operator on that pointer, well, it'll mess up the contents of the old generation, because that parent might get selected again in selection. Maybe that one parent has multiple children. But if we just copy the address, copy the reference, the pointer, whatever you want to call it, if you copy that over and make changes, well, everything that's aliased to the same thing is going to be changed. So what I mean is, be sure to do a deep copy. Be sure that you actually make a copy of the thing, of the string of zeros and ones, and not a copy of the memory address. Yes?
So just make sure to dereference before making any...
If you're using C++, yeah. Well, even if you dereference, you'll have to copy it still.
Yeah.
Yeah.
Like make sure you copy the dereference.
Yeah. Yeah.
Okay.
All of it.
Okay.
Any other questions or comments about that? Now that I explained it, raise your hand if you're like, oh yeah, I knew that. Okay, good. Good. All right. Yeah, all right. This is not this close. All right. So putting it together, really it's as simple as putting it all up. We need to create a new population. We initialize for 0 to max number of generations. Do a generation. All right, well, you know what? This is just one implementation. When you do yours, do whatever the hell you want. As long as it follows the high-level idea of a GA, of like, well, you've got these populations, you do selection, there's generations, you got crossover mutation. As long as you hack that all together and it works, I'm happy. Try your own implementations. In fact, I strongly encourage you to do that. Don't be boring. When you do your assignment 1, which I plan on having out today or tomorrow. I'd like to have it out today, but I've got 2 meetings after this, so I don't know if I'll get to it. I encourage you to just get creative, try something. And it doesn't matter if what you try gives you crap results compared to your friends, I don't care. Just explain what you did and I'll be very happy. All right, so let's spend some time actually looking at a genetic algorithm. So here is, at the back, can you see this reasonably well? Yeah, cool. So what do we got? Well, I've created globals, whatever. I've got population size of 10. In practice, that's a hilariously tiny number. It would never work very well. But to demonstrate the consequence of the values, I'm going to leave it at 10 for now. Chromosome length, 128. This is only going to matter in terms of the context of this problem. The chromosome length in TSP would be, well, how many cities are there? Here it's, well, how many zeros and ones do I want, right? So when I say 128, I mean, that's 128 zeros and ones, right? And I want to maximize the number of ones there. Maybe I should start with the smaller. Let's start with it like 32, right? Big number. No, let's do 64. There we go. And we're assuming this is an unsigned integer. Number of generations, 10. This is stupidly low. Never use 10. You'll never get good results. Select size, so this is like the pool size, because I'm doing tournament selection, because I almost always use that. 5. Why? Because we can play with this, see how it affects results. Crossover rate, 80%. Mutation rate, 10%. And then I've got a population and fitness. Okay, I've got 2 lists. They start empty. And the reason I've got 2 is because I like it to be lightweight, even though I'm still using Python, so it's far from being lightweight, I guess. But I like to have my array list of my chromosomes. So what is the population size? So I'll have 10 strings or arrays of zeros and ones of length 64. Okay? And then for each of those, I will have the fitness that corresponds to the index in there. So the population will be a list of lists. This will just be a list of values that correspond to their fitness, whatever fitness function I use. So initialize, what do we have? For I in range of the population size, create a new empty list. For each empty spot, append to it, what? Initialize. Something doesn't look right here. This definitely got out of order. All right, that looks better. There. Take the individual, append to it a random 0 or 1. Do that until I have all 64 zeros and ones. I have a list of that. And then I append it to my population. So this will run for a total of 10 times, I guess. So I will have 10 lists of size 64. So far, so good? At any point here, stop me to ask a question, because this is the most basic thing, and if anything's kind of like, wait, what? Let's make sure everyone's on the same page. And then fitness append 0, they start all with a fitness of 0 because why not? We'll calculate that and update those zeros eventually. Selection, for each, for selection size, randomly select a chromosome. Check if its fitness is better than the best fitness I've seen so far in this little pool. And then if it is better, I hold on to it. I remember that because that's the new parent, potentially. And if it's not better, I ignore it. And then I do that, I guess here, because I set it to 5, I'll look at 5 and be like, okay, so you were the best I've seen. Here's a new one, maybe it's no good. Here's a new one, maybe it's no good. Here's a new one, maybe it's better. New one, oh, it's better. All right, great, here's the parent. That's all this is doing. So far, so good. Yep. Why did I do it this way? Because you could have done it another way. I've seen people do selection where instead of doing like a pool of 5, maybe they'll do like a pool of 4, but instead of taking the best, maybe they'll do like, they'll take like the best 2 and that's the 2 parents. Or maybe what they'll do is they'll like pick 4, but these 2 will compete. And then these 2 are left, so it's kind of like a round robin, like tournament, yeah.
I don't know if this is getting a bit too high level, but if you take 2 parents from the same gene pool, is there any actual risk of like a computational version of like it says?
Yeah, it'll converge too quickly. So yeah, we'll see examples of that, and that's when the population loses like all diversity, and then there's no like chance for like good changes, unless it's just by luck mutations. Because if your population is all basically identical and you're doing 1-point crossover will make no difference, right? If I have the string 111000 and I do crossover with another string of 111000, it doesn't matter where you pick. You do that crossover, nothing's changing. So that's no good. Mutation's the only thing that'll work there. And I mean, a big problem when you talk about like the idea of like incest is a lack of like when you lose diversity, you lose like robustness in the population. It's funny because, you know, we're thinking of a candidate solution as like the best one, but we also kind of have to keep track of the population as a whole. And if we lose diversity, and maybe depending on the problem we're doing, something can change through evolution in terms of the definition of what's good. And if we lose diversity and it starts to converge on something that's good, but then the expectation, like what we're trying to maximize, changes slightly, this might suddenly become absolute trash and then the population can't really evolve to a better thing because it's converged. There's no diversity in the population, that's bad. It's true for these programs and it's true for populations in real life. We want our species to be genetically diverse, and it creates a much more robust species, like population. Okay, I've got a copy chromosome. This is just a verbose version of copy chromosome. New chromosome, probably could have picked a better variable name here. Create a new one that's like empty, and then for each one, copy over the contents, and then return the new chromosome. Okay, there. Single point crossover takes 2 chromosomes, randomly select an index, and then for the range of that index to the end, do a flip, right? And I'm doing that classic 3-variable exchange, right? You all know that. But of course, if you're fancy Python programmers, you can do it in one line, right? But don't worry about it. Bit flip mutation, randomly select an index, and then, I mean, here I'm getting fancy, I guess. I could have done like, if it's a 1, make it a 0. If it's a 0, make it a 1. I don't know, I wanted to show off and take the current value, add 1 to it, and then mod 2. So if the value is 0, and I add 1 to it, it becomes 1. And what's 1 mod 2?
1.
Yeah, 1. If the value is 1, and I add 1 to it, it's 2. And what's 2 mod 2? 0. There. So that's just a way to do a bit flip. Is it better than doing an if statement? Doesn't matter. Doesn't matter. It's just whatever. I'm showing off. Look how smart I am. Okay, now here I have 2 fitness functions. The 2 that we talked about. 1, fitness count ones. It goes through and just counts the number of ones. In fact, what it does is it sums up the values in that list. Because if I have a string that's like 1, 0, 1, 0, 1, 0, there's 3 ones, right? If I add 1 plus 0 plus 1 plus 0 plus 1, it's 3. So it's not like, oh, if it's a 1, count it. It's just, if it's a 1 or a 0, add it to the running total, because 0 doesn't make a difference. So yeah, there we go. Just count the number of ones. And then this one here, what am I doing? How did I do this? I start with an empty string. I do some string building where I take each 0 or 1 and convert it to a string and append it to that bit string. And then I convert the bit string to an integer, but it's binary. What? Oh, and I'm interpreting it as whatever. This just somehow magically, I can't remember when I wrote this what I was doing, but apparently it works. This will just convert the binary value to what it means as in regular old base 10 integer. Okay, so these are the 2 fitness functions. Any questions so far? Yes?
Will we be able to sit through this later too?
No, absolutely not. I will not share this code with you. But the good thing is it'll be posted on YouTube, so I'm more or less sharing it with you. I'm just making it jump through hoops to get the code, I guess.
Okay. Yeah,
Well, otherwise, your assignment 1's like done.
fair enough.
I'm already making it easy.
No, I know.
All right. I shouldn't say easy, I should say simple. There's a difference, right? And then calculate the population fitness. For those of you, raise your hand if you're used to Python. Raise your hand if you're not used to Python. Okay, well, by the way, in Python, you can pass a function as a parameter. Like I can pass to a function. You know you can pass like values to a function? Well, you can actually pass a function to a function. So I was being clever here, I guess. I've got calculate population fitness. So this is to do, the other 2 fitness functions are to calculate the fitness of an individual. This is to calculate the fitness of the whole population. So it's just a for loop that says, okay, for each population, each member of the population, calculate the fitness. It's just a for loop that calls the fitness function however big the population is. But what's cool here is I could change out what the fitness function is. I'll show you. Calculate population fitness. When I actually do it, I'll pass fitness count once. Or I can pass fitness, whatever it was called. Fitness int value. So it's like an easy way to switch it out. Cool. If you hate Python, that's fine. I thought it was neat. So yeah, calculate population fitness. So that all there, those are all the pieces. In fact, like look, calculate population fitness, probably gonna leave it more or less the same in this context. I've got 2 different fitness functions. If you have a third idea, great. This here, mutation, I don't care what the contents are right now. All I care about is I've got some mutation function. And you can change out this function for whatever you want. You could rewrite the contents of this, assuming it's a mutation operator, and like it makes sense, it's rational to use what you're doing. I should be able to run the code below and it should work just fine. See, it's like modular. All of these functions I can switch out for other functions that do the same thing in a different way. Am I getting across the modularitiness? I can't tell. If you're like, yeah, I know, move on. All right, that doesn't help me at all. But let's assume you are. Okay, so that's it. I've defined all those functions. Great. Now we got to put them together. Now I've got right here, I just have 2 empty lists where what I'm going to do, these are just bookkeeping lists, where what I'll do is for each generation, I'll keep track of the best value and then the average value of the average fitness value of the population, right? So we get a sense of where the best is and how the population average changes as well. Maybe it should be the median and not the average, whatever. You can do whatever you want. So let's see. Initialize, okay, that just sets it up. for I in the range of max generation, so if I set the max generation to 1 billion, this will run 1 billion times. It's just the loop for each generation. This right here is just to kind of like show me some progress. Every 10% of the way, it'll spit out a number. Because if I hit run, these algorithms can take a long time to run. So I want some like paging to show like, yes, it's moving along. Like there's like a progress bar. But I don't want to print out each generation number, because that's just too much. It's not very helpful. So this is a way I'm only going to print out ever like 0, 1, 2, 3, 4, 5, 7, 8, 9, 10. Whether there's 10 or 1 billion runs, or generations. Does that make sense? Okay, cool. Also, a lot of students don't know this. So if you write a for loop, where all you do is just like print out the contents, the printing is slow. If you write a for loop and tell it to print 1 every 10, it'll print, like that function will run like 10 times fast. It's the print that's slow, not the counting. So just FYI. You don't want to print out too much, because that'll actually slow down your program. Imagine the bottleneck of your GA being the printing. That'd be bad. So, all right, let's start over. Initialize. For each generation that we're going to do, calculate the population fitness. Create an empty list called new population. This will be like the new population. Just some bookkeeping. Append the max value of the fitness and the average value of the fitness. So you could effectively ignore this, but I'm keeping track of it because I'm going to plot some plots. Then, for I in range 0 to population size, count by 2. Right? So for each member in the current population, really that's probably not a good way to word it. For each empty spot in the new population. That's really what I should say. That makes more sense than what it means. So for each empty spot in the new population, count by 2s, I guess. What I'm going to do is pick a parent, pick another parent. Okay? Make a copy of those parents. Then what I'll do is I'll check. I'll roll the dice and check if I meet that 80% chance to do crossover or not. If I do, call the crossover function. And that crossover function will have the side effect on P1 and P2. Okay? Similarly for mutation, roll a dice once for each chromosome. Because remember, mutation acts on individuals, crossover acts on 2. And then when you're done, append the 2 new, potentially modified things that were selected to the new population. Yeah?
When doing the randomness for the crossover rate, the crossover rate is greater than the random number. Wouldn't that result in a lot more crossovers? Because there's a greater chance, like if it's 80%. Yeah.
Well, so if crossover is at 80%, and I pick a number between 0 and 100, or pardon me, 0 and 1, all the numbers 0 to 0.8, that's like 80% chance.
Okay,
Yeah?
yeah.
Okay. When you had me going like, uh-oh. Do I have it backwards? Yeah, so and then mutations, similarly, append them to the new population, and then when this for loop ends, meaning that we filled up the new population, just have the population now reference the new population. So it's like the old population, new population, copy everything over, population.
So what happens to the old population?
The old population, garbage collection.
What? Okay.
Raise your hand. Oh, crap. All of you. Okay. So, in most modern programming languages, raise your hand if you've heard the term garbage collection before. So, not all of you, and that's fine. So, in many modern programming languages, okay, who kind of hates deleting, like deallocating RAM in C++? Yeah, put up your hand, I know you do. It's terrible, it's annoying, right? Wouldn't it be great if the program, like if it just did it for you? Wouldn't that be great?
Yes.
Of course it would. That's what garbage collection is. It's a lot more complicated than that. Of course, there's a lot of things in it, how it keeps track, and how it knows when to deallocate the RAM. But the idea is, if I have an object in RAM, think of that array, right? In that example I had of A, B, C, D, F, G, H. If I ever made Z and W point to something else, and nothing referenced that array, I now have no way to get to there. Unless somehow I start doing a linear search through RAM and hope that I find it, but I mean, that's a terrible idea. So I've lost reference to it, meaning I can never access it again. So like languages like your Java, your C#, your Python, they'll be like, well, that's now useless, so we can just free that up. So I don't reference the old population. It'll exist in RAM. So garbage collection won't it often won't come along until it needs to go like, all right, let's free up some RAM. Because if it's still got a bunch of RAM, it's like, whatever, I can keep track of it. And then maybe every once in a while it'll do it. The downside of garbage collection is there is some computational overhead associated with that. But, I don't know. I'll take that over remembering to deallocate RAM any day. Anyways, yes, there we go. So this right here, that's it. And then at the end, once I'm done, I do one last fitness evaluation, the bookkeeping, find the best solution, which is whatever the best index is. And then I print out whatever the best solution is and show some plots. Any questions about this code? Because this right here, let me zoom out just a titch. How do I do this? This way? Trying to zoom out on a trackpad is not as easy. So really, in fact, I can zoom in. Nope. There. Perfect.
Is NP just new population? Did you have NP.pen?
No, NP is NumPy.
Oh, okay.
Yeah, I was arguably bad and renamed NumPy. Maybe I shouldn't have done that, I don't know.
I'm used to that.
You're used to that, yeah?
Oh, I'm used to being NumPy just because you have new population too.
Okay, so, who here calls NumPy NumPy? Because I do.
No.
It's way more fun.
Do you call sci-fi Sci-Fi?
No. I should, though. All right. That's it. Like, obviously there's the functions, but remember, the functions are the things that you can, like, plug and play. Initialize, calculate the fitness, ignore the bookkeeping. For each spot in the new population, do selection, make copies. Do I do crossover? Do I do mutation? Add them to the new population. That's it. Do that over and over and over and over again. And let's see what happens. Who wants to finally see it run? Put up your hand. Yeah, there we go. Run, GA, no. Okay, the first run is going to be really boring because I gave it some pretty boring values. All right, there, boom. There we go. I mean, it only ran for 10 generations. And the best result is this. Does that look like a string full of, or a list full of ones? Because we know that a list full of ones is the best result. And it's not. All right, so maybe what I'll do, so here the blue line is the best value. The orange line is the average fitness of the population. So we see over time, it gets better. So clearly though, 100 or 10 generations was crap. So let's let's make it 100. See what we get. Let's rerun it. All right, well there we go. But it's still not quite there, right? Right? But clearly we got, we're better off, I hope. Why? What did I change? Did I change? Something doesn't look right here. Yeah. Must have a bug somewhere in my code. Oh no. Here I was trying to get fancy and make some changes before class, and I may have just made a fool of myself. Why does increasing the generation size oh, look what I did. I reused I. I wonder if that's the problem. Let's do, do I even need an I here? No. Let's do this. Let's try that again. Cross your fingers for me. Uh-oh. Well, that didn't fix it, but something's definitely wrong here. New population dependent for each one of these. 0, 1. Well, something's not quite right. Why on earth? Let's do len of what was it? What did I call it? Of best solution. Okay. Len. Or is it what?
Is it the chromosome length?
Yeah, it looks like that's changing.
Because like in the first one you had it as 128, didn't you? And then you brought it down to 64. So if it was running, if you didn't maybe save it before you ran it, it might have still had the 128 in there.
Possibly. That's why I was trying to check the length, but now.
Oh, it's massive.
Oh, there we go. Okay. I think it's a numpy. No, it's a list. All right, so it's 64. All right, so it's right now. Something else was wrong. All right. So there we go. Maximizing. Let's make it. Let it run for 1,000. Nope. There. Hey, we got there. But look, clearly we got the best result. I don't know, at like generation. Oh yeah, about 200 it looks like. So here I've converged on the optimum, but let's see what happens. So look at the shape of this curve. Let's see what happens if I make mutation like 30%. I meant crossover actually, so that's good. Oh, it still works, but look, it took a little longer, right? I wonder what happens. Let's crank up mutation. Let's see what happens if I crank up mutation to like 80%. Yeah, get a sense of what do you expect to happen.
I expected it to be worse.
You expect it to be, well, okay. So, in fact, the best, look, there's a 0. So it's not the best solution, but you can see that it got to good solutions quickly, but then it like bounced around a bunch. We're out of time now, but maybe, when do we have class next? Thursday? Or tomorrow? Whenever we have class next, I think maybe we'll spend a little bit more time dicking around with the values just to see how it affects the results. And then we'll crank up, you know what, I'll do one last run. Feel free to leave. But let's see what happens if I do 1024. Oh, population size is tiny. Make it 100, make that 80, we're gonna put 1.
So I guess if you have a lower crossover rate, it kind of makes changes slower.
All right, so this one might take a second. Second or a few.
It's been longer than a few.
Define few.
3 or 4.
I don't know. I'm not comfortable with that definition. Yeah?
Something like this run faster if you had a dedicated GPU.
Depends. Look at that. It converged. It looks like we got all ones.
That looks very respectful graph.
Yeah, it's a respectable graph. It optimized 1,024 ones. Wrote ones. Wait, no, 124? 128? 1024. That's a lot, right? But, I don't know. Imagine I was doing that with a random search, randomly making changes. Do you think we'd get there? No. All right, now you can leave.